All right, good morning, everyone. Welcome to the first Friday in October. And I hope that you are all doing well. So today we're going to start talking about NMR. This is our last of our kind of theory talks. Then next week we'll start getting into reactions and using the things that we've been talking about with IR and NMR and Spartan and things like that, and applying it to some actual experiments that we're going to do. But today I want to give you the background on nuclear magnetic resonance spectroscopy, as well as some things about how to interpret the spectra. This is probably the most commonly used technique for synthetic organic chemists, or just any chemists, people who make things in chemistry. This is what we use. It gives us the most information. And if you think about mass spec and IR, they gave us really good information about pieces that existed within our molecule, but they don't tell us about what pieces are connected to what other pieces. And NMR will actually do that. So we're going to see, we get a signal in an NMR. So you get a peak, and that peak actually has a lot of information. It tells you, for instance, how many hydrogens you're looking at, and something about the electronic environment it's in, but it also tells you about what hydrogens are one carbon away. So for the first time, we have a way to look not just at a proton, for example, but one carbon away and find out how many protons are there. So we can start to make connections between the molecules. So we'll go through all of those things. We'll talk about what's happening with it as we go through, but just wanted to give you a little bit of heads up. Just to remind you this slide that we have seen already a few times. Right, we've got electronic, that's UV vis changes, vibrational, that's what we talked about last week. That happens in the infrared region. But now we're at this last one here, which is the radio frequency. That's the longest wavelength that we usually talk about in the electromagnetic spectrum. It's very low energy, but it actually affects the spin orientation of the nuclei themselves. So instead of moving electrons around, we're actually going to be affecting the nucleus. And we're going to learn something about that nucleus, because how much energy it takes to spin it depends upon the electronic environment that it's in. And as I said, what's next door. So we're gonna focus in now. I think this is our first technique that looks at the nucleus itself. And so we'll get some information about that. Okay, so this did get the Nobel Prize in physics in 1952. It's a very important technique. They realized it even as it was first coming out. It was actually discovered by physicists, and they were looking at the effects of the radio waves on the nuclei. The story, potentially apocryphal or not, I'm not sure if it's true, but is that one, I believe it was Dr. Purcell, they discovered this, but they weren't quite sure what to do with it, was having lunch with one of his colleagues who was a chemist, and said, you know, would it be useful to know about the electronic environment around a nucleus? And he was kind of like, yes, can you please give me that tool? And we went on from there. What we're going to look at mostly are protons and carbon-13. You can look at other elements. We have the potential of looking at fluorine in the coming weeks. Boron is another one that's fairly common, but they both have something called a spin plus or minus 1/2. It just has to do with the number of protons in the nucleus, the way it's arranged. We're not going to get into the details of that at this level here, but it is something to realize that you've got to, not all nuclei will show up in the NMR. And this works pretty well for us, especially for proton, because protons, 99% of all protons that exist in the world are proton 1, which shows up in the NMR. There's a few deuteriums. If you're lucky, you might find a tritium, but not very often. So pretty much all you've got that active. Carbon, on the other hand, right, most of carbon is carbon-12. So carbon-13 is the nucleus that will show up in the NMR, and it's only 1.1% naturally abundant. So that's going to affect the results we get, because we can only see 1% of the carbons. However, we're looking at big samples with billions and trillions and quadrillions, I don't even know how the numbers get, Googles of atoms in them. So, but we're going to come back to that natural abundance here in a little while. All right, so let's talk about a nucleus, and let's talk about spin. We do need to go back to physics for a minute, right? So your nucleus has a positive charge. It is a sphere, and so your sphere can spin one way or the other, just like the Earth can. And just like the Earth, you can create a magnetic field with that. So arbitrarily, we call one of these plus 1/2 and one of these minus 1/2. Doesn't actually matter which one's which because the molecule doesn't know what side's up. Usually spin up we call plus 1/2 and spin down we call minus 1/2, but that's just a convention because our brains like positive being up, but you know, the atom doesn't care. The main thing to realize is that if you have a spin plus 1/2, you're spinning in the opposite direction of something that's a spin minus 1/2. So it just tells us the relative ordering. Just like m sub s can be plus 1/2 or minus 1/2. In fact, they're kind of related to each other. That's a spinning electron. This is a spinning nucleus. Okay, so normally in a sample, your nuclei are going to be aimed all sorts of different directions. So in the absence of an external magnetic field, the nuclei aren't going to be lined up at all. They're just all totally random. But then what we can do is we can apply an external magnetic field. Now, for some reason, and I don't know why, but external magnetic fields are always given the abbreviation of H. There's not even an H in that word, so I'm not sure where they came up with that one, but it is. So in an external magnetic field, you see all of the nuclei line up, but, and this yellow is a little hard to see on my screen, but you can see some are going with it, some are going one way, some are going the other. Maybe the red arrows are a little easier to see. But so they either line up parallel or anti-parallel to the external magnetic field. There is a slight excess of those that line up with the magnetic field because it turns out that's slightly lower in energy. You can get them the other way, but you do get this here. So what we're going to do is we're actually going to find out how much energy does it take to flip that nucleus from one direction to the other. So we're going to take one that is going with the magnetic field, and we're going to flip it against the magnetic field, and then we're going to see how much energy did that take. We absorb a photon. It just happens to be a radio frequency photon, but we absorb a photon to do it. So this graph, I like to show this image because what's the energy change we're talking about? We're talking about going with the magnetic field to against the magnetic field. So how much energy does it take to cause the nucleus to flip and start going against the magnetic field? Because against the field is your higher energy state. Now, the amount of energy required is affected by how strong that external magnetic field is. And that's important because depending upon how powerful the magnet in your NMR is, it changes the amount of energy. So the bigger the external magnet, the greater the energy change, so the easier it is to see smaller differences. So you want a bigger magnet. The problem is they get really expensive. And so sometimes we have to compromise and say, well, I can't quite afford one of those because they are like $1 million or more. And so you can look at different things. So the stronger the magnetic field, the greater the difference in energy to cause it to flip, because you're essentially saying how much energy to push against that magnetic field. All right, so that's the energy change we're talking about. Instead of moving an electron from one orbital to another, we're causing the nucleus to flip its spin. Okay. And so another image that's really the same thing, but I really wanted to put it in that form that we've seen before. You've got the ground state, you have a high energy state, and you put in light that causes one of those nuclei to flip and comes up there, okay? But some terms you're gonna hear here, and part of why I mentioned this is magnetic nuclei are in resonance with the external magnetic field if they will absorb the energy and spin flip. So it's nuclear magnetic resonance that we're talking about here. And they go from the low energy to the high energy. Now, we'll say one thing. We're not talking about nuclear radioactivity. We're talking about the nucleus here. So an NMR, nuclear magnetic resonance, is looking at the nucleus's resonance with the magnetic field. Now, the problem is people hear the word nuclear and they get really nervous because they think glow in the dark and things like that. So if you've ever had an MRI, a magnetic resonance image, an MRI is actually a nuclear magnetic resonance image for people instead of molecules. But the word nuclear freaked people out, so they just dropped it. They just took it off the name. So it's the exact same principle. So if you go in and get an MRI on your shoulder, you're actually doing a nuclear magnetic resonance because they're looking at the nuclei and the spin flips, but the general public can't handle the word nuclear, so we just kind of pretended it wasn't there. But it is the same idea. So for those of you who are interested in medicine or anything, this is the same thing that happens in an MRI. So thinking about that. I love that people couldn't deal with that. Okay, so here's the basic. You need 4 things for this. This image is pretty old. I love this image, but you need something that makes the radio frequencies. For UV vis, that would have been like a light bulb. For us, we need a radio frequency generator because we're looking in that region. Then you've got the sample, and it's in a magnetic field. So for a sample that we do in lab, we just put a very small tube in there. And if you're doing an MRI, this has to be a little bigger because you put your person in here. But so the gap between the magnetic field is either a tube or a person. Then you need some way to detect it. And a CRT display, cathode ray tube. Nowadays, we probably would not use a cathode ray tube display. That's like old TVs and things like that. But anyway, it's pretty simple, right? You just need something that generates the energy, your sample in a magnetic field, and a way to detect that. So here's what some of these look like. The image on the left is the first Proton Nmr spectra that was ever taken of ethanol. And it was taken in 1951 at Stanford University. And so they saw 1, 2, 3 signals. Okay, so they got that. One was a little bigger than the other, and they were in different locations. Now, so that was a 30 megahertz magnet. Now you can take the same spectra with a 700 megahertz magnet, much more expensive, bigger magnet, but you get more resolution, and we can see that there's a little more information. We still have 1, 2, 3 peaks, but you can see that the peaks are spread out more, and there's some sort of a splitting going on. This peak is actually split into a triplet. That's going to become important later. I've actually never seen that one split that much before. That's kind of neat. But you've got the different information there. All right, so what do these look like? Back in the 1960s, this was what it looked like. Your classic science fiction movie type of scientific equipment. Here is the magnet that you put the sample in. It's an electromagnet, so you can turn it on and off in this case. And then the display is this little circle right here. It was just a little oscilloscope. And then I don't know what this is. I think this is the chart. That's the computer to help run it and control it. So that's where we were. A little more modern is this one here. It's a 60 megahertz. This is from the 1980s. I'm a little partial to this one because this was the first NMR that I worked with when I was an undergrad. And it's old school. You can't really see it because this binder is blocking it. But right there is a floppy drive. And we saved our spectra on floppy drives. You know the save icon? Yeah, well, that's a 3.5-inch floppy. These were 8-inch floppy disks. And each one could hold about 1, maybe 2 spectra. They were these ridiculous things. But it worked, and you could get that. We've gotten a little better. This is what they can look like now. I love this. I don't know who designed this, but some sort of product engineer said, let's just make it look like a rocket ship or something. This is a 900 megahertz spectra, or NMR. We have gigahertz ones. They exist. There are now above gigahertz that we're making. This is actually, if you notice, look how big this is. There's a ladder to get up to the top of it. They're very expensive. Part of the reason they're very expensive is to get these very high magnetic fields, we need to use superconducting magnets. And so it's as big as it is because you've got the magnet. The magnet has to be super cooled. So it's surrounded by liquid helium, and that liquid helium is surrounded by liquid nitrogen to keep it cold, which is then in the air temperature. And so you have to refill it every couple months with liquid helium. But there's also this beam that's coming out here. And this beam is coming out here because this magnet is actually large enough that it can start to mess with the nuclei in you. So it's not actually safe for someone to keep going in and out of this magnetic field all the time. So there's an auto sampler. So it actually puts the sample in for you so you don't have to walk in on a regular basis with that. And so it's kind of a nifty thing that we can see. And with those instruments, what can we do now? Well, instead of just looking at ethanol, we can look at this, cocochaxol, which is a microtubule inhibitor. And every one of these peaks down here corresponds to one of the hydrogens in this molecule here. Now, going from this to this is not easy. We're not going to look at anything this complex. This is what we have grad students for. Apologies to those who are on the call. This is a lot of work to get there. We're going to look at simpler molecules here, but we can do those things, okay? So what, or how does the NMR tell us anything useful? I said there's something about energy, but how does that energy get us to structure? Because ultimately we want to look at a spectrum and come up with a structure. So how do we do that? Well, as I mentioned already, mass spec and I are told about the pieces, but NMR will help show how they're connected. And we do that looking at the nuclear shielding and the shifts here. Okay, so let's look at this. We're going to put an external magnetic field. We're going to put our molecule in this magnetic field. But remember, the molecule has its own electrons, right? There are electrons that make up these bonds. So the external magnetic field will affect the motion of the electrons in the molecule, and it induces a magnetic field within the molecule. So the external field actually causes the electrons within the molecule to start moving, because electromagnetic, right, they're related, and generate their own magnetic field. But what's interesting here is that the induced magnetic field, and this is a physics thing, but it's induced in the opposite direction of the external field. So what you can see is this arrow is pointing down here, and this arrow is pointing down here. So the connection I want you to get here is that the electrons in the molecule, once you put it in an NMR, create an opposing magnetic field that push against it. So what you can see is, depending upon how many electrons are around this particular nucleus, will affect how much of a magnetic field is induced, or in other words, how much it pushes against the external field. So more electrons will push against the external magnetic field more. Less electrons do it less. And so if you have, let's say we put an oxygen on here. An oxygen is going to pull electron density away from the carbon, which is going to pull it away from the hydrogen. And that means that there's fewer electrons around this hydrogen to oppose the external field. So the amount of this induced field is dependent upon the amount of electrons around it. So we can start to see, is this proton near an electronegative atom or something along those lines, okay? And we refer to this as shielding, because we're shielding the nucleus from the external magnetic field by opposing some of it. So the induced field shields the nuclei. Effectively, the induced shield cancels out some of the applied field. And if you remember a minute ago, I said the amount of applied field changed the energy of the spin flip. So if you can cancel out some of the external field, then you change the energy of the spin flip. So that's really why one proton appears in a different place than another proton. Okay, so a stronger external magnetic field, therefore, a stronger energy is needed to flip the spin. That's what I just said. Okay, so chemical shift is the measure of that effect. Chemical shift's a measure of the degree to which the molecule is shielded. So we need to put numbers on it. We call it chemical shift. I'll show you in a moment why, but essentially what we did is we picked one signal, happens to be trimethylsilane or TMS, and we measure everything relative to that. How much is the signal shifted relative to the standard that we use? And so that's why we call it chemical shift. How much have we shifted it down based on that? Okay, so when you get a spectrum out of it, you get a scale. For Proton Nmr, it starts at 0, usually goes up to about 10. You can get further. I did some research on some molecules that are around 18, but most things are under 10. Carbon NMR starts at 0, goes to about 300. It just has to do with the different strength of the fields. But some terms here you want to get straight, because these just get used all the time in NMR. If something is upfield, it has increased shielding, that's to the right. If something is downfield, it's decreased shielding. Down is decreased, 2 Ds there, and that's to the left. So we'll say this is downfield of another signal. Or it's near something that's electronegative, so it's decreased the shielding, and therefore it shifts downfield. So more electronegative moves you more towards the left here. Okay. So the chemical shift is measured in parts per million, which is really weird because it's actually the strength of the magnetic field. but you can measure it in other units, but we usually use parts per million. All right, so as I said, we picked a molecule to be the standard. It's called trimethylsilane, or tetramethylsilane, excuse me, not tri, tetramethylsilane, or TMS. We used it because it gets a really strong signal, it has a lot of protons, and it is essentially completely inert. So we can put it in with other samples, and then the computer can find its signal and then measure everything relative to it. So it's essentially unreactive, which made it a really good standard to use. It's also pretty cheap. That's also a good reason to use it. So we put a little bit of TMS in with the sample, the computer finds it, and then measures everything relative to it. Right? So then the chemical shift, as I say, parts per million is then measured relative to the TMS. Just, my children go to the museum school, and TMS is now the museum school, not tetramethylsilane. So it means something different. Okay, so let me show you an example of this. So here's TMS. Here is a proton on a carbon, and there's 3 chlorines. Each of these chlorines are very electronegative, so they're stealing electrons away from the carbon, which says, wait, I want electrons too, so it steals it from the proton. So the proton becomes very de-shielded, so it is shifted downfield. Okay. And so it shows up here past 7. In fact, the effect is cumulative, we'll see. So how does the molecular structure affect that? Well, you've already seen that a little bit. Electronegative substituents move you more to the left. So here's some examples of some of them. So let's look at the protons here that are attached to a fluorine, oxygen, nitrogen, carbon, or silicon. And if you look at where they are, here's the silicon, the carbon, the nitrogen, the oxygen, and the fluorine. And if you notice, this goes exactly with increasing electronegativities here. So I have this reminder. It's what I just said, so I'm not going to read it to you again, but it's there for when you're studying later on. Just as you pull more electron density away, you end up shifting it more towards the left. Okay, so these are real molecules with real chemical shifts. And the effect is cumulative. So if you have 1 chlorine, it pulls a little bit away. If you have 2 chlorines, it pulls more electron density away. And if you have 3 chlorines, it pulls you all the way down there to 7.3 parts per million. So we can see that we have a hydrogen, but it shows up in different places depending upon how many chlorines it's near. This is this idea that we can start to get an understanding of what's connected to what as we go through here. Okay. Other things affect it, just the amount of electron density, right? So things that are sp2 versus sp3 are going to appear in different places because you've got that empty p orbital or the electrons in there. So what we find is that alkanes tend to appear less than 1. Alkenes appear usually in the middle, around 5. And then aromatics actually are always between 7 and 8, almost always. So what I hope you're seeing here, similar to what we saw in the IR, is that different types of groups, different functional groups, appear in different locations of the spectrum. Now we have to be a little careful because the effect is cumulative, right? So what I talked about just a minute ago, near 1 chlorine puts you here at 3, but near 3 chlorines puts you down here. So each of these groups are essentially, if it were on its own, where would it appear? But if I took this and I substituted one of these hydrogens for a chlorine, I'm going to shift things even further down, right? So you connect those. So here are some common regions. You should know just these general regions. I'm going to show you in a minute a correlation table that is similar to what we saw with IRs. But in general, to just help you out, if you've got a saturated carbon, it should be down around 1. The allylic, right, that's 1 away from the double bond, right, that should be a little higher up. Halogens move you in general here into the middle range, although again, if you have more than 1, you can move yourself further down. Vinylic, and then aromatic. This one here is really useful for us, right? How many compounds you see in class are aromatic, right? There's a whole bunch. It's really common. And so that's going to be a pattern that's going to help us identify things in the NMR. Then this correlation table, which is a little more detailed, would be provided for you. So this gives you a little more idea of some specific things and where they are. Alcohols are a little bit of a problem child. We'll talk about those in a minute. Notice a huge range, somewhere between 2.5 to 5. But actually they can appear as low as 1 and as high as 12. So alcohols are a little odd, but it gives you some details. So again, what you're attached to affects where you appear left to right in the spectrum. That's the chemical shift. All right. So what all information is in an NMR spectrum? And it has a lot. IR was essentially just where the peaks are and a little bit about their shape. NMR is the other way. You've got 4 pieces of information that you get out of an NMR signal. Or out of an NMR spectrum. The first is just how many signals you get. Second is where those are. That's the chemical shift that we just talked about. Then how intense they are. That didn't matter in IR. It does in NMR. So the intensity tells you something. And then as it turns out, the splitting pattern also tells you something. So I'm going to go through each one of these. Although actually I've already done number 2. But just to give you an overview when we're here. The number of signals is how many types of hydrogen you have, or types of carbon. The location is how electronegative groups they're next to. Intensity is how many protons there are. And then the splitting pattern is how many neighbors they have. And this is the thing that's new to NMR. So I'm going to talk initially about proton NMR. I'm going to focus that. The same things work for carbon or boron or other things, but I'll just be using the term proton because that's kind of the most common one we use. All right, so we've already talked about kind of location. Let's talk about number of signals. In NMR, we talk about chemically equivalent protons. They're protons that have the same electronic environment. They're near the same other things. And so to give you an example, when we look at this molecule here, we have 2 types of protons. We have the green protons that are on a carbon next to a triple bond on one side and an oxygen on the other. And then we have the red protons that are just next to an oxygen. So their electronic environments are different. So all of these protons will show up in this signal here, and all of these protons will show up in this signal here. So the number of protons tells you how many types of hydrogens you have, for example. So I'm also going to include throughout the presentation these TLDRs, just to kind of summarize it. 2 types of protons gives you 2 signals. We'll say chemically equivalent protons. That's what we're talking about here. Okay. So just to go back to Chem 202 and 150 for a minute. Remember cyclohexane? Everybody's favorite? If you're in Dr. Weinsteig's class who can draw these things like without even thinking, I don't know how he draws his chair so well, but he does. But one of the things that's interesting about this is we talked about the axial versus the equatorial peak. At room temperature, the ring is flipping back and forth and back and forth and back and forth. And so those 2 protons actually average out and you only get 1 signal. They're chemically equivalent because half the time they're axial and half the time they're equatorial. But if you cool this thing down to 90 degrees below 0, you lock it in place and it can't exchange anymore. Because remember, all equilibrium constants are temperature dependent. And so what happens is this stays axial and this one stays equatorial, and you actually do get 2 signals in the NMR. So we can see that ring flip happening or stopping depending upon the temperature that you're at, and whether or not these average together and behave like they're the same thing. So just kind of a throwback to something you'd seen before, and everybody's favorite organic molecule of cyclohexane. Well, I don't know if it's your favorite molecule, but there you go. Okay, so number of signals is how many types of protons. Where they appear is their environment, how electronegative things are next to them, all right? Then the next thing is integration. And integration tells us how many protons are represented by that signal, all right? So this peak, how many protons does this peak mean? How many protons give rise to this peak? They are simply the area under the curve. However, these are usually very, very sharp curves, and it's hard to measure the area, but computers are good at it. So the computer does this for you, for this method. For GC that we'll see in a couple weeks, we have to do it ourselves, but here we do it. So the area under each peak is proportional to the number of protons causing that peak. I emphasize that because in a minute we're going to talk about next door neighbors. Here we're saying the protons that give you this signal and how many there are. Now notice that it always gives you the ratio, not the exact number. So when I look at this line, this trace that's going through here, this black line, That is the integration. That's the computer figuring out relative how much is each thing to each other. And when it comes out, it says that relative, the height or the area under this peak is 1 to 3. So it will always be a ratio. And now in this particular molecule, if you look at it, it's actually 3 to 9, but that's the same ratio, right? So 1 to 3 means it's 1 proton to 3 protons, or 2 to 6, or 3 to 9. So you just know the ratio. So integration only ever gives you ratio. It might match, it might not, but it's always going to be a multiple of that. So we know how many types of hydrogen we hit. We know something about their electronic environment. And now we also know how many hydrogens there are in each, relatively in each signal. So we're getting a lot of information about a molecule. I'm going to do some full examples here in a minute. I see some of you are getting a little glassy-eyed, but we'll get there. And then the last piece of data, which is I think really what makes NMR so useful, is telling us about the neighbors, this splitting. Okay, so what happens here is you've got a proton that you're looking at. Now there is a proton what we call next door. That is 1 carbon away. It only works for 1 carbon away. So we're on the next carbon over. Those protons can be lined up with or against the magnetic field. And they're close enough that they affect the proton you're looking at. So you're looking at proton A. Proton B on the next carbon over could be spinning with the field or against the field, and that will end up causing your proton to be affected, that signal to be affected. And in fact, every possible option exists there, right? Because we're dealing with billions of molecules. So you're looking at proton A, about half the time the proton next to it is spinning with the magnetic field, and half the time it's spinning against, and that ends up splitting our signal. So the next door neighbor splits the signal into smaller peaks. Okay, so let's look at this. So this triplet down here represents 1 proton. It represents proton A. So this is proton A. But the next door neighbors, so 1 carbon away, these next door neighbors, there's 2 of them. They both could be with the magnetic field. One could be with and one against, or one against and one with, or they could both be against the magnetic field. So you've got 3 options, and this energy affects this one. So when they're both with the magnetic field, it pushes it downfield. When they're against the magnetic field, it pushes it upfield. When they're split, it's right there in the middle. So the thing I want you to try to kind of get here is this triplet represents hydrogen A. It's a triplet because next door to it were 3 or 2 other protons. So you've got 2 things. You've got the signal itself and then the splitting of that signal. The splitting is due to the nearest neighbors. Okay. We can also then look at the hydrogens that were B hydrogens. And we get a doublet here, not because there were 2 of them. That would be the integration. But because there's 1 proton next door, and sometimes it's with the magnetic field and sometimes it's against it. One other thing I want to say really quickly, why are these 2 equivalent? It looks like this one's near this one and that one's further away, but remember it's a single bond and it's actually rotating in space all the time. So that's why those end up balancing out. You've got the 2 propellers that are spinning here. And so that's why both HBs are equivalent. Okay. All right. So moving on. So what you noticed a moment ago, I said is if there were 2 nearest neighbors, we got 3 peaks. If there was 1 nearest neighbor, we got 2 peaks. So if a signal is split by n equivalent protons, it's split into n plus 1 peaks. And we got really creative here. This is called the n plus 1 rule. Ooh. Essentially, however many peaks you see it split into, you subtract 1 to tell you how many nearest neighbors there are. So 1 nearest neighbor gives you a doublet. It actually follows Pascal's triangle. It's real, it's not just math. I always love that. Pascal's triangle tells you the relative intensity of the peaks in the triplet or the quartet or something like that. And so you've got that. Okay, so number of equivalent protons causing the splitting, and then the multiplicity or what that peak appears. So if there's no protons nearby, it shows up as a singlet. If there's 1, it's a doublet. Likewise, quintet, quartet, things along those lines. So the TLDR is the number of peaks minus 1 equals the number of nearest neighbors. Okay, so let's just look at a couple other splitting and intensities here. I want to walk you through what we already know. So 4 types of information, remember? First one was number of signals. Well, I've got the methyl protons and I have the CH2 protons. So I get 2 signals. The second was chemical shift. The pink protons here are next to a bromine, which is electronegative. So they got shifted further down. So they're like 3.5. These methyl protons, the blue ones, are not next to a bromine. So they're closer to 1. Okay, so that's number of signals, the location, then the integration. If you look at the integration here, it's a little hard to tell on this graph, but that's a 2, and then that's bigger, so it's 2 to 3. So that's number of protons causing that signal. So because this is a 2, I know there are 2 protons causing the signal, but it was split into a quartet because there were 3 next door neighbors. So I know something about the signal and its neighbors. Likewise, the blue ones, it has an integration of 3 because it is 3 protons here, but it got split into a triplet because there were 2 next door neighbors. Okay, some of that makes sense. Some of it just comes. NMR is one of those things. Think back to when you did Lewis structures, and you did Lewis structures, and when you first started with Lewis structures, they were really hard, right? Because you're like, wait, what do I connect to what, and how do I do it? And then you just practiced, and it got better. NMR is going to be the same thing. You look at this, there's a lot of information in here, and you're like, there's too much at first, but you're going to start to look for patterns. As you play with NMR and you do examples, start looking for patterns. It's going to help you out. And I'm going to highlight a couple of these here in just a second. Oh, I do want to say one thing really quick. The distance between these, the splitting here, tells you information that we're not going to worry about yet. Wait about a month, we'll talk about that. But there is something to be said about how far it gets split. We don't need to worry about that yet. Okay, so I just said this. NMR becomes much easier with practice. Look for patterns. Here's some patterns. If you have an etho group, right, that's really common, CH3, CH2, that means that you're going to have an integration of 2 to 3 that's split into a quartet and then a triplet. That's what we just saw. Or this type of a group is actually really common. These 2 methyl groups are spinning around, right? So they're equivalent. So they represent 6 protons. So that's this. And they have 1 nearest neighbor. That's this proton in the middle. So they get split into a doublet. But then this one little proton in the middle, okay, it integrates to 1, but it has 6 nearest neighbors. So it should be a septet. 1, 2, 3, 4, 5, 6, 7. On these multiplets, these little ones on the outside sometimes are hard to see, but we're gonna try to look. So if you see this quartet triplet with integration 2, 3, you probably have an ethyl. If you see this septet doublet, you probably have this group here. So that's what I mean by looking for patterns. All right, so let's actually do something with this. Here is an NMR. Yay, it's a spectra. Is this 1 bromopropane or 2 bromopropane? And you have enough to figure it out. So think about it for a moment. Just to help you out, these are the structures of 1 bromopropane or 2 bromopropane. I won't tell your teachers whether or not you could do that in your head. So let's think for a minute. If you have an idea, just throw it in the chat. All right, 2 bromoprotein. Yay! Thank you for the 3 of you who are brave to start with it, or more than that. Brave to start with it, and you are correct. So we can actually get to this multiple ways. First would be number of signals. And there's 2 signals here. So we should get, this has a methyl and 1 hydrogen. So we should get 1 signal for these methyls and 1 for this. Here we should get a signal for the CH2 next to the bromine, another signal for the CH2 that's near that, and then another signal for the methyl. So this should give us 3 signals. That should only give us 2. Okay, right away we know what it is. Likewise, the integration here should be 1 to 6. 1 to 6, oh, 1 to 6. And the splitting, this should be a septet, that should be a doublet. In fact, it's the pattern I just showed you a moment ago. And then we get that. Okay, all right, so there's something real with it. Let's look at another one here. P-Methoxypropiophenone. I gave you the structure for that because, I would have to look that one up. So here is the splitting for P-Methoxypropiophenone. Couple things that we notice. One is we've got a couple of peaks down here in the 7 to 8 region. I want you just automatically, if you see two sets of peaks out there, you've got an aromatic ring. Just know that. Those are the aromatic protons. And then we've got a singlet here at around 4, a quartet around 1, and a triplet around 1.5. So let's think about this for a minute. Think about what you've done. I can just tell you, but it's not the same as you thinking. So I've got another one for you thinking about it for a moment. Which color of signal, pink, green, blue, black, probably represents the methyl on the far left, this methyl out here? Because we've got a methyl here and we have a methyl here. All right, blue, green, green. We're getting a little more greens here. Let's think about it for a second. First of all, what are the two options it can be? I said it was a methyl, right? So let's look at our integration. 1 to 1 to 1.5 to 1 to 1.5, because remember, it's always a ratio. Well, you can't have 1.5 protons. So we're going to have to double all these numbers to get the actual number of protons. So this is going to be 2 protons to 2 protons to 3 to 2 to 3. So that means that the methyl groups are the green and the black groups. Those are our 2 methyls, because they're the ones that integrate to 3. Then I look at it and I say, okay, the only real difference, well, I got 2 things that are different. This one's split, this one's not. So the black one is split, the green one isn't. And the green one is further downfield, and the black one is further upfield. So I look at this molecule and I got a methyl here on the far right and I got a methyl over here. Well, the methyl on the far right is next to an CH2. So that means this one should be split by these nearest neighbors. Okay, so that means it's probably going to be this one. This one does not have any nearest neighbors, so because there's just an oxygen here, so it should appear as a singlet. So that one's probably going to be green. Also, it's next to an electronegative oxygen. So it's 1 proton away from an oxygen. This is 2 carbon away. That's only 1 carbon away. So that should shift this downfield, should send it down to the left. So it is the green one. And it's the green one because it's not split because it has no nearest neighbors. And it's further downfield because it has next to the oxygen. So a lot of information to help us with there. And then we already answered that one. It's the black one there. Okay. So we can go through that process. So what else does that tell us? Well, this integrated to 2, and these also integrate to 2. Now the location is very different. These are down here 7 to 8, so those are going to be your the ones on the aromatic ring. These 2 protons versus these 2 protons, and then this CH2 group is going to be the blue one here, and you can tell that as well because CH2 it's next to a methyl, so it should be split into a 4. Okay, so we're starting to see some of those pieces there. All right, some other things to think about. Proton to C13 NMR. They're very similar. It's just, are you looking at a proton or are you looking at a carbon? Except remember that carbon was only 1.1% abundant. And the effect that that has is that both give you information about the number of types of carbon and their location, but the integration and the splitting become unreliable. Because if you have a carbon that's C13, the chances of the one next to it also being C13 is only 1%, so 0.01. And so the splitting just becomes unreliable. And then the integration, because you're only seeing 1% of the peaks, is also unreliable. So we don't look at those 2. We actually turn that off. So C13 has no integration or splitting because it's only 1% active, so those are unreliable. But you do still find information about how many types of carbon and where they are. Show you an example of this. Here's a C13 Spectra. So we have bigger range here. Let's look at this molecule here. Chlorine, carbon, 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 carbon. So we've got 1 chloropentane here. And you notice we get 1, 2, 3, 4, 5 signals. Now there's these little things here, but they were, it turns out, the solvent. That was the methylene chloride. That was just, or CDCl3 chloroform. But we've got these carbons, and it turns out that each one of those gives us one of those peaks. So every one of the carbons shows up on their own. So you can start to see number of equivalent carbons. The closer they are to the chlorine, the more they are next to an electronegative element, so the more downfield they are. Okay. Spacing's a little different. We're not going to get into that. There is information in there, but we're not going to worry about that. You can spend your entire career doing NMR if you want to. I don't, but okay. So what do you do when you're faced with an NMR spectra? There's a lot of information. I just spent the last 45 minutes telling you about all the things that NMR can tell you. And it's a lot. And trying to keep track of it all at once is really hard. So Professor McGill came up with this table as a way to help you just kind of organize it. When you first start working with NMRs, I recommend you fill this table out. As you get more practice, you'll be able to fill this table out in your head. But don't try to do it when you start. Take the time to write it out, because it is like this huge jigsaw puzzle where you're trying to figure out all 4 of those pieces of data at the same time and build a structure or build a molecule. Don't forget to calculate unsaturations, because that can remind you, hey, I need a double bond or something like that, or a ring. And then each table, or each entry in the table has this, right? So the chemical shift to the peak, what its integration is, do I have to double it or not, or something like that? And then the multiplicity, and then how many nearest neighbors that are. Okay, let me show you this in use. So let's look at C4H8O. If you look at this molecule, we can do the calculation on unsaturations, and we find there's one degree of unsaturation. So we either have a double bond or we've got a ring. Then I fill out for each one of these. Okay, at 1.1, that's the middle of this. There's a peak that has an integration of 3, and it is a triplet. Now, if I look at the integrations, 3, 3, 2, 3 protons plus 3 protons, that's 6, that makes 8 protons, which is how many we have in the molecule. So that means my integration is equal to the number of hydrogens. But if there were 16 protons in this, I'd have to double everything. Okay, so that's just kind of what you do there. So what do I know? Well, this triplet, that means the connected nearest neighbors is what we have, right? So this was, just to remind you, it is chemically non-equivalent nearest neighbors. That's the multiplicity minus 1. Okay, so in other words, if that's a triplet, you have 2 nearest protons. If it's a singlet, you have none. And if it's a quartet, you have 3 nearest protons. So somehow this molecule, and believe it or not, this is enough information to figure it out. You need to have 3 protons. Well, what gives you 3 protons? Well, almost always that's a methyl group, right? Because it's very hard to get 3 equivalent protons that are anything but a methyl group. It can be done, but it's hard. So this is probably a methyl group, and this is probably a methyl group. This is a methyl group next to 2 other protons. This is a methyl group next to nothing. This is a methyl group, sorry, this is a CH2 group that's next to probably a methyl group, okay? So, hey, right, once again, we've got an ethyl and a methyl, probably. But somehow we've got to get this methyl group to be not next to anything else. But we do have to have 4 carbons, okay? So let's look at, whoa, let me jump ahead, at this structure here. And this is what I'm going to propose for this. So I needed a methyl group, and then I needed a methyl next to a CH2. But these had to be separate from each other because they weren't splitting each other. So I put the carbonyl in between, and that double bond is my unsaturation. Now you can see right away that actually something that might have helped would be an IR, right? Because if you had the carbonyl peak, I know to do that instead of an alcohol. But you've got that. All right. So the slide I skipped was, what does it mean to annotate an NMR? So you will be asked to annotate NMRs. All it means is you put the Lewis structure on, and you draw an arrow to every signal and where that comes from on the molecule. So that's what I've got here. So the annotated NMR is the NMR with the Lewis structure, and then arrows indicating that this signal came from these hydrogens, this signal came from those hydrogens, and that from these. Okay, so that's what it means to annotate the NMR. It doesn't explain how you got what you got, but you need to be able to do that because chances are you're probably going to be asked that. Hint, hint. Because we want to make sure you understand where you got there. But an annotated NMR just shows you that. There is a shorthand notation that if you read the literature would say something like delta 2.45 2H quartet, actually Q. And it's a shorthand notation for journals, so you don't need this whole thing. But using the shorthand notation implies that you can take that and reconstruct the NMR in your head. We're not there. So we're going to use this version of annotating as opposed to the literature one, because the literature one is kind of, it's deep inside chemistry. All right, so I mentioned this already. This becomes easier with practice. I think that's the 4th time I've said that today. And I want you to understand that. I remember back when I was a sophomore learning NMR. And I remember going to office hours with Dr. Louis Quo. We called him Uncle Louis for some reason. I don't know why. But we would go to these office hours at night. And I'd be looking at all these things. And I'd be like, well, if I connect this and things, And he would just look at the structure and go, oh, you just have this. How do you do that? And it came with practice. I can now do that. I could not do that at first when I started. It will seem intimidating. It's okay. With a little practice, it becomes easier, just like the Lewis structures did, okay? Look for these patterns. Then the other thing I just need to give you a warning about is alcohols. Alcohols are NMR's problem children. Because the proton, it's not really very acidic, but it's somewhat acidic. So that proton can pop on and off, and that affects it. So because it can exchange with a solvent, and actually amines can do this too, but because it can exchange with the solvent, it usually doesn't take part in the splitting. So if you're looking at nearest neighbors, don't count alcohols. And it can show up anywhere between 1 and 6 or as far as 12. So alcohols are a little weird. So just kind of know that it doesn't kind of fit in with our other patterns there. All right, so let's look at one. C6H12O. There we go. You guys know what it is yet? Okay, I don't either. Well, okay, I do because I wrote the PowerPoint presentation, but I have to think about it. I have to work through it. For one thing, I need to zoom in and see. A lot of times these are really small, and so we zoom in and we see what we got. So I've got 1, 2, 3, 4, 5, 1, 2, 3, 4. I've got, ooh, this thing here is actually a doublet and next to a triplet. All right, so let me look at this, calculate my unsaturations, use the formula, comes out to be 1. So I got 1 unsaturation. Then I look at my table, and I just fill in this table. And I really, really recommend doing this when you start. The other thing I recommend is anytime you do look at a structure, try not to use the condensed structure. I know it's really good. You're like, oh, I'm in my 3rd semester of chemistry, and I know what I'm doing now, and I can use condensed structures. You're trying to look at the protons, which is what we don't write on a condensed structure. And so trying to use condensed structure just makes your life more difficult. Right? Take the time to write out the protons. Okay, so you can go either direction, doesn't matter, but at 2.58, I've got an integration of 1. I got that from the computer. Okay, so I look at my integrations here. 3 plus 6 is 9, 10, 11, 12. That matches the number of protons. So I know that that's also, the integration is also the number of protons it represents. So somehow I have to have a single hydrogen. I got to have 2 hydrogens. I got to have 6, probably 2 methyls. And I've got to have 3. Then I look at the multiplicity, and I look at this one, and it's 1, 2, 3, 4, 5. Anytime I have 5 or more, I'm a little dubious about it because those small peaks on the end sometimes can get lost. So I'm going to say it's a quintet, but I'm going to remind myself, like, it's pretty small. We'll see if it's actually that. And then I have a quartet, and then I have a doublet, and then I have a triplet. And so then my chemically non-equivalent nearest neighbors, if it's a quintet, that'd be 4, and then 3, 1, and 2. And here's where I look at this, and I have a little bit of a problem. All right, so this proton, this signal needs to have 3 nearest neighbors. All right, I got one of those. Let me start it. This has to have 1 nearest neighbor. I got one of those. This has to have 2 nearest neighbors. I got one of those. This has to have 6 something has to have 6 nearest neighbors. I don't have anything with 6 nearest neighbors. My number of protons here does not equal my number of protons here. That's a problem. So what that tells me is that this is probably not a quintet. It's probably a septet, and it probably represents 6. And that small little peak on the ends just got dropped off. I only noticed that because this column did not add up to this column. That's which point I said, we're probably missing something. All right, so what do we know? Now, we know that we have 1, 2, 3, 4 types of hydrogen. We know that the group of 3 hydrogens has to be next to 2 hydrogens. and the group of 2 hydrogens is next to 3 hydrogens. Well, that's probably the ethyl group. So I was looking at these 2 rows right here. I said my 3 protons were next to 2 and my 2 protons were next to 3, so I'm going to guess that that's probably an ethyl group. The other thing I notice is that I've got a group of 6 hydrogens here, and they're next to one other. So they have to be next to a single proton, and it's likely 2 methyls. So how does that help me? Okay. Well, you see, we got pieces, but we don't just have pieces, we have connections between the pieces. All right, so let's look at it here. Here's what I'm going to propose. Now, let me come back for a second. Actually, I jumped ahead. The other thing is I've highlighted this in red and this in blue because these 2 groups cannot be directly next to each other. Why can't they be next to each other? If they were next to each other, this CH2 would be split by these 3 protons and a proton on the other side, but they're not. So there has to be something without a proton in between. Likewise, this 6 hydrogens, if this one is split into 6, okay, it can be next to the 2 methyls, but it can't be next to anything else. And that's why I knew to put in this carbon in between my 2 groups. So my ethyl group, and then my methyl with the 2 methyls, my CH with my 2 methyls. Okay, so if I annotate this, I'm going to say, okay, that's probably my doublet, that's probably my septet, here's my quartet, and there's my triplet. Okay. Again, this is a lot of information that I'm throwing at you all at once. However, it is important enough to do this that now you will start to use this in class. You will use it in 204 lecture and lab. You will use it beyond. It's just that useful of a technique. But we needed to have a decent amount of chemistry under our belt before we could start to really understand this technique. Okay, I think I have, yes, one more example. And I alluded to this already, is can you use IR and NMR together? And certainly you can. Almost always you do. If you take an NMR, usually you take an IR or a mass spec as well. And so let's look at this one here. All right, C8H10O. Calculated unsaturations comes out to be 4. Now, as a trained chemist and by trained chemist, I mean somebody who's focused on those patterns, when I see 4, I think, okay, this could be multiple double bonds, or it could be an aromatic ring. Because an aromatic ring is a ring closure plus 3 double bonds. So that's just a really common thing. But I look at this right away. Okay, what do you see in the IR? Well, we got a big old peak out here. I've got an alcohol, right? And there's nothing here, so there's no carbonyl. All right, so I had to do something with this oxygen. What do I do with it? This tells me right away somehow I got to put an alcohol on there. And, well, there's only 1 oxygen, so I don't have to worry about it. But if there were 2 oxygens, I check for carbonyl. Okay, then what do I see right away in the NMR? All right, well, I've got a lot of peaks, but I have 2 peaks down here between 7 and 8. And that tells me aromatic ring. Okay, so that's the only thing that appears all the way down there. So 2 peaks between 7 and 8, it's aromatic ring. And actually the IR backs that up because these 2 peaks right here are the aromatic CH double bonds. You can get that, but you can see that in here. And then aromatic ring would be our 4 unsaturations. So right away, just by glancing at the spectra, I know I've got an alcohol. I know I've got an aromatic ring. Well, aromatic ring, that's 6 of my carbons right off. Okay, well, okay, that's a lot of my molecule. And an O and an H, okay, so that's a good number of it already. And then I got a couple more signals that I have to deal with here. So let's do those. Let's look at them. Let's zoom in a little bit more. All right, I've got a triplet out here, or a doublet of triplets, it turns out. This one is this, it's a little hard to tell. And then this here and this here. Okay, so we can fill out our table. I'm not going to spend a lot of time doing it, but a couple things I will say. The splitting in an aromatic region is very unreliable. There's really weird things that happen because of ring currents and stuff like that. So the fact that it's a triplet doesn't tell me a lot. I'm going to write it down, but it may or may not tell me anything. A lot of times aromatics appear as a doublet of doublets. So just be aware, they're a little bit weird. The other thing I kind of notice is that's really broad. Okay, so we know we have an alcohol, we know we have an aromatic ring. The ring has 5 hydrogens. Okay, how do we know that? All right, so let's go ahead and fill this in. So I fill this in, and then I look at it and I say, okay, the aromatic region, that represents 5 hydrogens. So what does that tell me? That tells me that there's 1 substitution on my aromatic ring because it has to be C6H5. Right, let that sink in for a second. If I had 4 aromatic protons, I would have 2 groups off of my aromatic ring. I don't know where they are, but it would tell me how many groups I have off the aromatic ring. But because I have to have 5 aromatic hydrogens, C6H5, I can only have 1 substitution. So it's got to be, everything else has to be pointing off the ring in 1 place. Alcohols are often not seen, but if they are, they're broad. So that tells me that's what this thing is. And as I said, they don't partake in the splitting. So what do I know? I know I've got aromatic, that's 5 of my hydrogens. Then I also have to have 2 CH2s and probably my alcohol at this point, okay? And so I'm gonna propose this. All right, I said the aromatic ring had to have a single substitution, so everything else has to be hanging off there. I needed 2 CH2s that were each next to 2 neighbors, so they were both triplets. Now again, if you look at this one here, this is splitting it. This looks like it should also split it, but alcohols don't take part in the splitting usually. And so I can annotate it, and I can put all these things in place. Now, I drew these 2. You usually can't tell which signals go to which in the aromatic, so just pick ones, you're fine. And you can do that. As you practice this, if you see a molecule now, you should look at the molecule, introduce yourself, and then try to think about what its NMR probably would look like. You can predict NMR spectra in Spartan. Now, Spartan will not give you as much of the splitting. Well, it gives you the splitting, but it does it theoretical. So sometimes it's a little bit off. ChemDraw also can predict spectra. In fact, ChemDraw is really, really useful because it doesn't have to take time to do the calculation. So if you draw a molecule in ChemDraw, highlight it, then you go up to the structure menu and you look at the bottom, it says predict the Proton Nmr or predict the C13 Nmr. In future weeks, we'll use that and we'll talk about which technique is better and why. But it's a good way to practice. If you want to try to build an NMR and say, did I get it right? You can do it. And in fact, it'll show you all the assignments. So it's kind of useful with that. Okay. So that is actually the end of my presentation. So we're at 11:04 a.m. All right, we fit NMR into an hour. I want to remind you again that you're just going to need to practice. With that. So, oh, I just saw there's a question in the chat. Why is the OH group not more downfield? Because alcohol is weird. It depends upon which solvent you do it in. And what they didn't tell us in this is what they dissolved this in. If you dissolve it in D2O versus methylene chloride versus benzene, the alcohol moves to all different places because of that interaction with the solvent. So that's really what's affecting that location more than anything else. With that. Okay. All right, I'm going to stop the recording now.